Okay, well, we are at the top of the hour. I will go through some quick welcome and instructions. So, welcome everyone. My name is Jacob Hayden, and I'm the program coordinator for Safer Sim at the University of Iowa. Safer Sim is a Tier 1 university transportation center with the research priority of promoting safety, and our webinar series features the research projects from within our center. Thank you for joining us today. We will have time at the end of the presentation for questions and discussion. Attendees can use their microphone to participate. Feel free to mute yourself during the Q&A session if you'd like, or feel free to use the chat box at any time to participate. We will hold those questions till the end during that Q&A session. Um, I do want to mention too that this video is being recorded and will be shared online afterwards as well. And with that, I would like to welcome our presenter for today, Chengbo Ai from the University of Massachusetts-Amherst.
Okay, I guess I'll get us started. Thank you, Jake, for the introduction. And today I'm going to share a little bit of what we have learned through the projects on quantifying the impacts of a situational visual clutter on driving performance using video analysis and eye tracking. And our research team actually include me, myself, and Dr. Michael Nodler, and two of my graduate students, Xingyang Ye and Qing Ho, and it's been a pretty great efforts. Especially, I'm quite appreciative of the Sim family as well as my students as hardworking. And More acknowledgement, although they're I want to acknowledge their efforts or help through all the process regarding the simulator data, regarding the digitization of the video clips, as well as some of the online help through the GitHub community, through the different labeling tools. And without them, it's this project is really hard to get any results really. Um, so here is the outline of today's presentation. I will just quickly introduce the background and the motivation of this study, the objectives of the study, and then introduce the research data, and then comes to the methodology that we have developed, share with some of the results and the discussions, and then summarize the entire efforts, and then hopefully can shed some lights about the future works of by extending the study into the different other projects. So for many of you may have known, a situational visual clutter may affect really the perceptions of the driving environments and then subsequently impact the driving behaviors. And the many psychological studies and the cognitive studies have shown that already. And then, but it's although it's very important that people really want to investigate those effects, but sometimes it's very hard, especially in the context of a driving environment, because basically we're dealing with all aspects of different contributors to this kind of effects, the vehicles, other road users on the road, and the road infrastructures and entire environments. Also, the situation is dynamically changing. So it's not just, oh, I took a snapshot of this situation and then it doesn't change for next 10 minutes. No, it's changing every second or even sub-seconds. So it's very important to realize, although it's important, it's still challenging to sort of get a full insights of what is situation visual clutter would mean to us. And then that's, I guess, what really motivated us to look into this area. And some of the just these pictures shows some of the complicated scenarios. Although in this study is we are using a sort of a simplified version of that, but in reality, actually, we are dealing more complicated situations, like really the cluttered dashboard, the cluttered scenes, and with different messages, and also the cluttered different modes of traffic, and also the surroundings. And then imagine these are no longer video, no longer images, but videos. It's dynamically changing. Then it's really for the drivers, it's a lot to digest. And then that's we think maybe we can have a little attempt to see what we can do a little bit about these. since we are safer sim, everybody is super familiar with the driving simulators and the experts on that. And then really we find that the driving simulation systems enable really better understanding of the visual clutter through comprehensive and synchronized data collection. And then with all of the video clips, eye tracking systems, and then the detailed vehicle status recorded. And so actually you can have a very comprehensive data to look into that. However, not every single driving simulators like are born equal or are the same. Some of the low cost of legacy systems are still in place. I mean, they are well suited for the targeted research. However, their data may not be synchronized and may not be comprehensively collected. And then it created some kind of a challenge to really how can we leverage those data to review some of the what we want to learn about the visual clutter, about the situational video clutter. And then I want to note, and everybody probably share the same thoughts, is like simulation is really expensive. Not in terms of equipment, they're expensive for sure, but the participants and the efforts made into creating those scenarios, they're really, really, I mean, valuable data. And if we can think of a way that can really leverage those valuable data, although they are not purposely, especially for situational visual clutter, and then if we can have some analytical tools to leverage those valuable data, I think it's worthwhile for us to look into this area. That's really what motivated us to write the problem statement and then actually move on to this project. Okay. So regarding the objectives, and then there are really two aspects of it. One is try to develop a new video analysis model that can quantify the complex and dynamic driving scene. And then here I highlight the video analysis because many of this, the data that we collected, and besides those spreadsheets, besides of the recorded vehicle behaviors, I think the most important or easy to visualize the data would be the video data, and I think that would be our cutting angles to execute this project. The other one is really to employ this development model so we can quantify the impacts of the situation visual clutters on the driving performance. And then if we can link them to some of the eye tracking data, then I think it would be reassuring that our model seems to be working in that direction. I mean, by all means, we not intended to comprehensively study all the linkage and the connections between the video analysis results with all kinds of other data. But we do want to like go into this and then use eye tracking data as an example to show, oh, probably this would be a good way for us to further extend the study into other data as well, or look more eye tracking data and the video analysis data. Okay. So the research data in this project we consider slightly different from other projects is because we didn't collect any. I would say this: we didn't collect any, like conduct any new simulation or driving simulator data collection, but rather we use a existing research data that being collected through the previous CIFRSIM projects led by Dr. Mike Nodler, and then titled To Trust or Not to Trust, a simulation-based experimental paradigm. And then because this effort actually accumulated a very good repository of data, including 80 subjects, and we think with video, with eye tracking, as well as the entire driving simulator recordings. And we think this would be a very proper data to use. And if we can work with this data, and then apparently this data is not purposed for situational clutter analysis, but if we can use this data, very likely we can move on our models to other data as well. Okay, and then on the bottom is just a slightly screenshots of the different videos and also the text data for the driving simulator and the eye tracking visualization of different vectors of those eye tracking data. And that's the research data we are utilizing in this study. Okay. By the way, if you have any questions I know my time is short, but if you have any questions, feel free to stop me, and then I can maybe elaborate more on that, or you can wait until the end of the presentation. Okay, regarding the methodology, and really it's a four-step approach, and it's pretty sequential. Like I said, we want to focus on video analysis because that's the biggest, we think is the most um, like demonstrable piece of data that we want weekend analysis. So that we propose this four-step approach. The first one is the image segmentation. I will go a little bit details of what step means and the embodies of different methods. And the second one is color and objects profiling. And then third would be by process those different videos, and then if we can come up with some quantification measures or metrics, try to measure the situational visual clutter. And then the step four is whether we can link the eye tracking data with it to really demonstrate that this model can work or not. Okay. So regarding the first part is the step one, this image segmentation. And I know you probably sick and tired of looking this kind of all different kinds of deep learning architectures. And we were introducing a particular architecture called the fully convolutional neural network architecture, and then use there are some jargons that I've mentioned, but I mean, if you have questions, I can explain a little bit more. We're using FCN8, using the VGG architecture, and essentially, in a nutshell, we want to really create masks or segmented images into different aspects, different pieces. So each piece, or we call it each blob, can represent a meaningful body. Here's the vehicle, here is the road, here is the interior of the vehicle, here's the dashboard, things like that. And the reason why we use a fully convolutional neural network comparing with a convolutional neural network is like we want to maintain their spatial information as well, so that all these segmentations are correspond to the coordinates of the image, and later on we can translate it into the eye tracking locations. Okay, and just to give you a snapshot of that is the video that we capture is something like this. And in the step one, we're not too ambitious. We just want to use that to frame a neural network just to segment it into very simple, smaller pieces. But I mean, the pieces are still pretty general. You can see the interior of the vehicle, maybe the dashboard together with the operatable wheels, some of the dashboard in the central control, the rear mirror, and then in the exterior, essentially just the pavement and something else, right? So you can see we only segmented into four classes in this particular step: interior, screens, pavement, and other exterior features that we don't really segment it further at all. And then there's a reason for that. I'll explain this later. And screen and other exterior features will require subsequent processing in step two. And for those of you who are not quite familiar with deep learning or neural network, fully convolutional neural network, things like that, is like we need to create a database, labeled database for executing this kind of segmentations. And the challenging part is like how can we accumulate enough data? And what with the parts that we are focusing on is we want to, because in the realistic or naturalistic driving scenes, there are a lot of studies on this already. All those scenes are realistic or from the real world. I mean, all those models can plug and play. And in this case, we want to leverage those models. However, this is slightly different here. We have to create our own model or utilize the term called transfer learning to establish our model based on those, because the simulation scene here is not realistic. It's not from the real world. Although we can understand what the trees are, the houses are, the neural network may not necessarily understand that unless you gave them enough training data in these kind of a particular scenes, like a sort of a quote unquote fake scenes in our simulation. And then that's That's why we don't want to go ambitious. So we basically clustered all the exterior except the pavement, which is very easy to identify, and then into the same cluster. And then later on using the following steps to work with those detailed classifications. Okay. So the second part, step would be the color and object profiling. And then again, I don't want to show any equations here. There are three regions, if you remember, there's three regions we want the subsequent processing, right? Which actually are information rich, like the region one, which is besides the pavement, everything else are really crowded in that region. Region two, which is our dashboard indicating the status of the vehicle, which is very information rich. And then also region three would be the entertaining systems or some central control systems for our vehicle, which is also information rich. We cannot just say, oh, region one, two, three, because they're much more into it. That's why we wanted to introduce two pieces additionally to further detect or identify the information within it. For region one, I mean, just this little blue, light blue color region, we further utilize a slightly different fully convolutional neural network for the object identification. There's a subtle difference between segmentation and object identification. I won't go too much detail, but here this model can give you actually the individual objects within the scene, and but only processing with the region of this region one. Okay, for region two and three, which is the interior of the vehicle, but the screens, and then you can see neural network may not work. I mean, we didn't try that because use the same framework is because the subtlety of these differences between like a different like the readings of the different meters, and which neural network is really not a good tool, especially using a video which is only 960 by 720. It's really hard to do. However, the distinguishable feature actually related to the colors. So we leverage existing methods for the color segmentation so that we can segment it into different pieces or different blobs for the screens or for different buttons or options in this central controlled entertainment systems. And now after this step two, essentially we are having a pretty good segmented scene of this video clip. Regardless is collected, like in a general term, regardless is from a simulator or from as well, we are having a really a meaningful blobs of different things, trees, houses, like greens or pavement or dashboard with a different blobs. And these actually will, if you think of the first image that are shown in the first slides, and you can see all those clutter situations, right? This, you can imagine this would be a simplified version of those cluttered items. Although much more simplified, but still can reveal some insights about, oh, how cluttered this is. And then with both exterior and the interior setups, this will becomes somehow intuitively can be meaningful, right? And then we go to the step three, which is how should we really quantify the video clutter from this really this kind of output. We figure out two ways to do it, and I will explain a little bit in the next slides of why we only use these two measures. One is the number of the blobs. When I say blobs, meaning the number of really the color blocks in these segmented or identified videos, video frames. And then this essentially represents different types of number of objects that you're seeing where you're driving. The larger the number is, which means a more cluttered scene you may want to have to understand because it have a different meanings of objects that force you to see and then eventually understand. And then also the complexity of the blob, which essentially is really how complicated that individual blob is. Here, this blob gave you a mask, which means, oh, this speedometer is this dark blue blob. But what we look is utilizing this boundary, we go back to the original image and try to understand really how complicated the really how this blob is formed in terms of complication of edges, uh, like how complicated it is. And then we use a measure called the norm of the gradients. Essentially, it just we accumulate all the gradients measures, quantify the gradients within that blob, and then average them out. And then now by the number of pixels. So now you have a really a unified measure that says, oh, within this blob, how complicated it's gonna be. And for those of you who are not really familiar with the gradients in the image, you can consider in any natural scene like the edges of what you're seeing, how complicated it somehow reflects how complicated really the scene is. And the more, I guess, the larger the number is, or the larger the complexity is, means the more cluttered objects to recognize. Um, then we think of these two would give us a really generalized idea and also specific idea about each blobs. And then um, now we can have some kind of a measures. And of course, we treat exterior and interior differently because we think people grab the information from the exterior of the car and the interior of the car differently. And we can sort of have really simple measures for these parts. And then you can see that here's the exterior, here's the interior, and we only have two measures for each parts, right? Number of the blobs and also the complexity of the blobs. And then complexity of blobs, like I said, each blob can represent what will be the text, like the texture within the measure, the better gradients. Okay. And I want to note here is in this study, the situational video clutter is quantified only by these two measures because first one is the segmentation and detection accuracy. It's like we cannot require our algorithm because we only have a very limited training samples for these quote unquote fake scenes or the simulation scenes to train our model. And then the accuracy actually is not that good. And you can see, actually, you can tell some of the boundaries are not really performance as good as what is the algorithms are performing on the real world data, which has millions of training data that work on that already. The other part is availability of the eye tracking calibration, which means it's like, do we really need to go very nitty gritty of those any edge by 1 pixel or 3 pixels, or we just gave a region of that because your eye tracking devices try to pinpoint where your eye is looking at may not be accurate enough. And then it's overkilling it if we really go into very detail of segmenting it into very detail. And that's the reason why we were using only these two measures. And then sort of, we're not even measure the individual quantification for the trees or for the pavement. We clustered them together with only two measures. And then I mean, through the performance evaluation, we find some interesting results, but definitely I think it's worthwhile to further explore other metrics or other indicators, but still, I mean, just to be noted, in this study, we only use these two measures. Okay. And the step number 4 is the eye tracking linkage. It's like we want to link the eye tracking information, which essentially represents what is the psychological condition or psychological status of the driver, and we want to link that. And then there are two parts. We only use the calibrated sensor, which is like luckily in those 80 participants video, the video data and the eye tracking data are synchronized and calibrated, which means your eye tracking, like really the location can be pinpointed to exactly where the pixel is representing in that image. So we took advantage of that. But go back to our original motivations. We want this to be general enough so that we'll also explore the uncalibrated sensor, and then we reviewed a bunch of literatures in those regards. However, we didn't pursue that because just we didn't collect much of the data. But for those of you who are interested, and I'll be willing to share some of other, like can be an entirely different study regarding the pulse of the video spacing, and then calibrated like offline calibration with the eye tracking, and then yeah. But with this step, essentially what we can achieve is like every single eye trackers can be associated with some pixels in the video clip, and then that those the pixels in those video clips actually have been processed by us with some meaningful measures, and then we created an entire linkage. Now every eye tracking status, saccade, fixation, like a blink or any other measures actually can be associated with a context, and then that's what we want to achieve. Okay. Let's see if there's time. Okay, I'm a little bit quicker. And so we did a bunch of testing. The first one is just a segmentation detection accuracy, and in the entire data sets, we actually processed almost 6 million frames in all those video clips, and was split into 10%, 20%, and 70% for training, validation, and the entirely testing of the model. And then my undergraduate students spend a lot of time utilizing this tool, which I think is very useful. Maybe some of you have been using it already, the computer vision annotation tool, just to establish some of the ground truth and help me to do some of the validation as well. And I can report, if you recall the step 1 and step 2 of this methods, the segmentation here in a nutshell, accuracy would be 0.857, and the detection would be 0.821. And for those of you who's not familiar with the IOU, is the intersection over union, which means like our traditional term of a false negative and false positive, and you can see basically they're overlapping with each other. The overlapping part will be the intersection, meaning my true positive cases, and then the denominator, which is the union of those, which includes some of the false positives. The bigger the number is, the closer to 1 the number is, the better the data is. So we think in the mid 80s or lower 80s is okay. But you probably seen some of the deep learning methods can achieve like higher 90s. Again, we are limited by the number of training data, but also we want to make sure, we want to emphasize that, do we really need the data accuracy? Because here we are really estimating the region for different objects or different blobs. We're not going to like a nitty gritty of 1 pixel or 2 pixels of error. So we think this will be definitely can be improved, but we think it is meaningful enough here. Okay, and I will also share with you why we think so. Okay. Then we process all those video, and then we have all those quantifiable measures for those number of blobs, complexity of the blobs, and then we want to see how those can be inferring the driving performance or the status of the driver. And then we do, I highlighted here the sample quantification, quantitative measures. I listed the sample is because this is just a sample we think are meaningful, but I think the entire segmentation and the entire analysis of the videos can really do more performance evaluations in the future. Okay. The first thing we are doing is the eye tracking events, which is the fixation and the saccade versus the region. And when I say region, if you still recall, there are three regions that we are focusing on. Remember, the exterior, which is informational rich, region 2 and region 3, which are the screens, which are also informational rich. And here are what we find by accumulating all those frames and then the regions of the eye tracking devices. And we find in region 1, I mean, like quite a bit of people are doing fixation, and which we think is quite interesting, and also pretty high percentage for saccade as well. So for region one, it sounds like people are doing high acquisition task and high search task at the same time, looking for different things. When they look for different things, they want to understand what those things are. For region two and the region three, you would think they would do the same thing, but apparently people are doing less searching and less acquisition, especially for the region number two, which we find interesting. And we suspect it's because the driver is well understand like all of those blobs of all those blobs of objects. They understand what they're doing, and they really don't need to do see a lot of those informations all that often or search more information. So the region two seems to lower activities in those regard. And then for region three, and then people are like median acquisition and median searching because some information infotainment systems or central control systems may change slightly. And then in this particular case, I think that also some kind of automation features enabled when the data was collected. So the screen may change slightly. And that's why there are more activities of fixation, the saccade as well. So we find this already pretty interesting by just rudimentarily use the regions that we identified from the video. And then we move on to the next part. It's like, what we have the eye tracking events, we get the situation. Now we can the location, which is interior and the exterior. And then we have the situational visual clutter measures, right? If you remember the number of blobs and the complexity of the blobs. So we want to look into whether we can quantify these of situational cluttered with the measure that we extracted from the video clips, right? Remember only the number of blobs and also the complexity of those blobs, and then measured by individual blobs here. Okay, and here are what we found. The first thing is the number of blobs versus the eye tracking events, which is essentially we're focusing on fixation and saccade. And you can see for the interior, which is entirely those gray area, also the wheels and then the screens. And you can see for the fixation and with the more numbers of blobs, definitely there's a trend of increasing. But overall, if you ignore the very last one, because this one has a bigger sample, you can see overall it's pretty flat, meaning like people don't really perform, I mean, their eyes not really fixating on anything in particular, even the number of blobs increased. I mean, that's sort of interesting, right? But also call back what we suspect is like people are pretty familiar with the interior, pretty familiar with their odometers and their speed dials. So they probably don't see all of those things like quite often, or want to see those, check those things quite often, or with a longer duration, including also they not needed to search more information. And it seems like the saccade is also pretty flat, which I think is reasonable. And for the exterior, we find something quite interesting is for the fixation, you can still please ignore the last bars. These bars has a larger number, and then it's not quite meaningful. But if you consider the trends from these bars, you can see like, oh, the fixations with the number of objects appearing in your video, it sounds like the fixation activities are somehow reduced, or that there's not much of fixation, but people are doing saccade quite more. And then does it mean we're not sure like whether it means like people are searching more information in the cluttered environment or not, rather than like engaging on a particular objects and then try to understand it. But I think that is telling that maybe the number of blobs quantify using number of blobs quantifying the clutterness probably can have revealed some insight already. Okay. The other measures, like really the how complicated that objects may be. And then here you can see is from 0 to 1, which is normalize the complexity of those gradient summation. But you can see for the interior, still, I mean, it's pretty flat, but more complex that blob is. You can see the fixation seems to be slightly higher in the higher range of that the complexity, and then I mean the saccade, and the fixation seems to be slightly less. But overall, it's still pretty flat. I mean, I don't see like a 11% versus 8 or 9% is the difference that much. Still, call back to the my original thoughts is like probably people don't really look at those things at all, regardless of whether it's complex or not, because you already know. Or even if it is complex, it doesn't matter because you're really familiar with that really dial of your odometer. There's no need for you to really look more or dwell on longer to understand it. Okay. For the exterior, it's a little more interesting is with the more complex things. I mean, we find it the fixation actually is dropping, which if you interpret it straightforwardly is, oh, if the more complicated that blob or that object is, people looking at it dwell like fixated less, and that's something I again we didn't do any validation because these are legacy data, but I think that's something interesting that can be reviewed from the model that we developed for just the video analysis. And also you can see that the saccade, the percentage is like seems like on the lower end and the higher end, which is like the complexity of the objects either is extremely too big or extremely light, like really simple. And people really don't do that action at all. And only in the middle, they're probably doing those like a browsing effects quite more, and which we find it quite interesting as well. Okay. Again, I mean, these results are sample results that we think is kind of revealing the video analysis model seems to can, I mean, have the capacity to reveal some interesting results. But again, we're not validating it. The reason is like we don't have the like the uh, I guess the post survey regarding these behaviors. But still, I think by given more time and resources, if we want to expand this study to other more driving simulations analysis, we probably can validate this kind of anticipation. But so far, we find these performance changes just indicated by the eye tracking events. It seems to be seems to be go with our intuition. Okay. A quick summary. I know I'm a little late. We developed a new situation clutter model and then try to objectively quantify the complexity and then that dynamics seen of the driving simulation clips. And also we explored some of the sample and potential use case of these models, this model, and then just to try to, we hope really can support more analytics on the legacy data, which we find we are sitting on a gold mine, but because it wasn't purposed for the particular goal of the situation clutter, we're not really utilizing it. But now with this tool, we hope that we can utilizing those legacy data or archive the data more. And for future studies, and just three quick things that I think I mentioned to evaluate other deep learning and the image processing approach. And then, and for better, I use the term consistent because here, even if the method is not performing like in high 90s, as long as it can consistently perform all the videos across the board, I think it's a valid method that can be plugged into our methods. And then also to investigate the impact of the uncalibrated eye tracking data, which we didn't do in this study, but we hope to do it in the future analysis. And then the very last one is hopefully through the validation and through other more data analysis with more videos, and then we will hope to review more insights on how situational visual clutter may affect the driving performance. And with that, I mean, any questions will be welcome. I think I'm a little longer on this. Yeah, thank you.
Thanks, Chengbo, and yeah, no worries about the length. That is great, great detail and interesting work for sure from UMass. Um, we will open it up for any questions or comments here, and I'm glad we do have your email up there as well. So if there's something that you want to take offline, by all means, feel free to
Yep.
reach out to Chengbo. I'll give it a couple moments here. I'll give my usual reminders that this presentation will be available online on our YouTube channel and our website in the next couple of days, and we will share that link with all of our registrants here today. So feel free to forward that to any other colleagues that may be interested once you receive it. And then we do have another webinar coming up next week already on Tuesday, and that will feature some work for the University of Central Florida. So we're excited for that one. We will send more registration information about that actually tomorrow with our full stack of webinars coming up this summer. We do have a question come in asking what is region 3, please. I remember it is in the median search level.
That is correct. Let me pull that back here, right here. The region three is the central screen of the vehicle, and it is in the median acquisition and the median search in terms of percentage. We find the fixation and also the saccade.
Excellent. Well, I think this is, oh, here we go. So a couple questions coming in. I think a follow-up to that question, what was the driver searching that region for?
That's interesting. I cannot answer you for sure, but one suspect that we will want to in this data collection, actually, like I said, there are some automated feature enabled, and actually there are some screen flashing or change of layout of the screen, and then we observe from the video, and we suspect that that is what they are searching for information for, although in the name they just there's something changed in their peripheral vision, they find those and then they not necessarily look at it, but those are the things that we want to I guess we are suspecting. um,
Awesome. We have another question that came in. First comment, awesome work, Chengbo. Understand that this was done using post hoc analyses of video data. What is the viability of this model on real-time analysis?
that's a tough question actually. It's possible because uh, the segmentation process actually is not that slow. I cannot say real time, but actually half a 1, 2 to 5 frame per second is feasible. But then again, I think how to utilize it in a real time setup, that's I think we need to more discussion. And the other thing that I want to point out is the project's target, we didn't optimize any processing speed. The target is we want to post process existing data. And then for what we are having right now, I mean, I don't know, Anuj, if you're talking about the sensors that we are having, everything so far we have been synchronized already. So this study may not be as meaningful as applying this to let's say a game box type of like a really simplified version of simulator. But I mean, I would love to talk with you like what's the use case of if you want to do some real time analysis. Even let's say we don't go broad for all the objects, we just specifically for one object, signage or bicyclists or whatever. So, oh, cool, we have new toys. Great.
Awesome. So it sounds like future conversations will be happening at UMass with this project. But I think that might be a good place to wrap it up there. Like I said, we will send this out by the end of the week once it is available online. Chengbo, we will have your email address CC'd when we
Okay.
send that out, so people can just respond to you directly from that if interested.
Yeah, sounds great. Here's my information, and then feel free to reach out to me, and then yeah, we can discuss more.
Perfect. Well, thank you everyone, and you'll see more about our future webinars coming up tomorrow and coming weeks too. Thank you,
Okay,
Chengbo, and we'll see you all at the next ones.
thank you.